Hey everyone, this is my Teach the Doc for Chapter 4. This one took me a long time to do, and I made a lot of mistakes along the way, so just ignore my chicken scratch. But for the first one, the complete ionic equation, everything was soluble here, so it was able to be separated using the solubility rules and wrote in the missing phases. So it ended up being 2K 3 plus, which is aqueous, plus 2PO4 3 minus, aqueous, plus 3Fe 2 plus, which is aqueous, plus 3Br2 minus, which is aqueous, yielded 6K plus, which is aqueous, plus 6 Br minus, which is aqueous, plus Fe3 2 plus, also aqueous, and then plus 2PO4 3 minus, which is aqueous. Yeah, so everything there ended up being soluble, and that's why the phase is all aqueous for all of them. And I just used that table that was in the book that was recommended there, and just separating out the ions and their charges, and it all ended up adding up. Still use the solubility rules here. So the only ones that were soluble in water were Na3PO4 and then C1O3. The KOH one is kind of interesting. So the potassium is normally soluble like with other things on its own, but the OH minus is specifically it creates a solid with compounds in group 1, and that is K, so that one is not soluble. And then the next one is showing how the cations and anions would swap in a double displacement reaction. So instead of, AgNO3 plus BaCl2, and just swapping those, so you get AgCl2 plus BaNO3, just doing that double displacement. But the AgCl2 is actually a solid, so that would be the precipitate that forms from that reaction, while as the BaNO3 is still aqueous. The conversions here, so you're just taking the moles per substance and how it reacts with the other one. So it takes, ooh, I wrote that wrong. See, catching myself every time I do this. So there are 3 moles of O2 per 2 moles of CH3OH, and then vice versa. There's 2 moles of CH3OH that react with 3 moles of O2. In the yield, there is 2 moles of CO2 per 4 moles of H2O, and then like vice versa, that would flip too. That was helpful using these problems on the back. So using the dimensional analysis, we converted 3.56 moles to the number of moles of oxygen that were required. So just using that same conversion ratio. So there are 3 moles of O2 that react with 2 moles of CH3OH. So I just used stoichiometry and did 3.56 moles times that conversion factor, which ended up being 5.34, which thankfully was the answer. And then the number of moles of water formed when 15 moles of O2 react. So for this one, again, I just used some stoichiometry, but then I also just realized that the coefficients could be added differently. So just use 15 moles of O2, and then there are 2 moles of CH3OH per 3 moles of O2. So that was going to react with 10 moles of CH3OH. And then I realized I was doing too much work. And so then I just realized I could just multiply the coefficients by 5, which still ended up working with the conversion ratio. So 10 CH3OH plus 15 of O2 yielded to 10 CO2 plus 20 H2O, which I got here. So I think there's just a couple different ways to do that one. And then this one took me forever, so I was using the wrong limiting reactant. So, but I ended up taking the 95 grams of Br2 over 1 times 1 mole of Br2. I'm just converting it over to moles, and then the molar mass was 159.8, so put that on the bottom, and then solving for that. So 1 mole of the C6H8Br4 per 4 moles of Br2, because that's it's a 1-to-4 conversion ratio there, and then times it by the molar mass of C6H8Br4 over the mole of it, just to get rid of the crossing out factors, and that equal to 59.4 grams, which is the theoretical yield. And then to get the percent yield, you take the actual yield over the theoretical yield, and we were given the actual yield of that 55.5. So 55.5 over 59.4 times 100 is 93.4%. This one also took me forever. Let's see what I ended up doing here. So watching the video and a couple other videos, I was able to get like kind of just a different way to figure it out that was easier for me to understand. So I just went ahead and did my conversions of the milliliters to liters, and simplified it, so I got my like liters in here instead of having it be like a lot of conversion factors in the stoichiometry, because I remember even in high school that would throw me off, so it's just easier for me to convert right away out of the equation. So we were calculating the concentration of a 49.1 ml solution of BaOH2 with 50 mils of 2.95 molarity of HCl is required to react completely. So I took what I was given, which is the 2.5 moles of HCl per 1 liter of solution, and then we had 50 mils of the HCl, excuse me. So that ended up being 0.05 liters. And then the ratio of moles, it was 1 mole of BaOH2 that was reacting with 2 moles of HCl taken from that equation up there. And then times 1 over my conversion of the 49.1 mils to liters. Ended up getting the decimals here, but it ended up working out to 1.5. So it was 1.5. And again, that took me way too long. But I kind of learned by trial and error as well, and then that's why I liked having the answers on here, because I was like, okay, like if my answer isn't right, I could figure out what in my my like problem solving was wrong, and then I was able to use a lot of different resources to figure out the answers. So thank you.